In the next series of modules, we're going to discuss mortgage mathematics and mortgage-backed securities. We're going to look at mortgage-backed securities because they will give us an example of the process of securitization. That is the process by which new securities are created from pools of underlying loans or mortgages. So we're going to begin in this module with basic mortgage mathematics and an introduction to the mortgage market. Recall that according to SIFMA, the Securities Industry and Financial Markets Association, that in the third quarter of 2012, the total outstanding amount of US bonds was $35.3 trillion. Now, if you look at this, you can see that the mortgage market actually accounted for 23.3% of this total. So the mortgage markets are therefore huge, and they played a big role in the financial crisis of 2008 and 2009. And that's one of the reasons we're going to talk about mortgages and mortgage-backed securities over the next few modules. It is interesting to understand what they are and how they are constructed, and some of the mechanics behind the basic or most standard types of mortgage-backed securities. Mortgage-backed securities are a particular class of what are called asset-backed securities. These are assets backed by underlying pools of securities such as mortgages, auto loans, credit card receivables, student loans, and so on. The process by which ABS, or mortgage-backed securities, are created is often called securitization. Here's a picture of how securitization works in the context of mortgages and mortgage-backed securities. What we have here are 10,000 different mortgages. Each of these mortgages corresponds to a different homeowner. What we do is we combine these 10,000 mortgages into one big pool of mortgages. So these 10,000 mortgages form the collateral for the mortgage-backed securities that we will create. Here we have what are called tranches, tranche A, tranche B, tranche C, and tranche D, and tranche E. We won't worry what these are right now. We'll see an example of this later on. But basically what we're getting at is the following idea. We combine these 10,000 mortgages into a pool of mortgages or a pool of loans. And then from this large pool, we can construct a series of different securities. Each of these securities are labeled tranche A down to tranche E, and the payments, the mechanism, the risk characteristics of each of these securities are very different, even though they are all built from the same underlying pool of loans or mortgages. So this is the process of securitization. Now, you might ask the following question. Why bother with securitization? So why securitize? Well, a standard answer to this is that by securitizing we are enabling the sharing or spreading of risk. So it is in order to share risk. If you like, any one of these individual mortgages might be risky by itself. Maybe the owner of the home will default and not pay. So any one mortgage by itself might be too risky for a small bank to hold. So instead what they can do is they can pool all of these mortgages together and then sell them off to investors who are willing to bear that risk. We will look at some examples of mortgage-backed securities, but first we must consider the mathematics of the underlying mortgages. Now, there are many different types of mortgages, both here in the US and in different parts of the world. We're going to consider just level payment mortgages. Level payment mortgages are mortgages where a constant payment is paid every month until the end of the mortgage. So that's a level payment mortgage, but there are other types of mortgages. For example, adjustable rate mortgages are mortgages where the mortgage rate is reset periodically. And in fact, these kinds of mortgages actually played quite a big role in the subprime crisis. So as I said, we're only going to consider level payment mortgages, but that's fine. It's important to note, though, that mortgage-backed securities may be constructed out of other mortgage types as well. The construction of mortgage-backed securities, as I said in the previous slide, is an example of securitization, and the same ideas apply to asset-backed securities more generally. And so that's one of the goals of these modules in mortgage-backed securities. It's just to show how the process of securitization might work, how you can combine pools of loans, be they from mortgages or other markets, credit cards or auto loans, for example, how you can combine these pools of loans and create new securities out of them. That's a very big part of the financial industry, and so we're going to discuss that, but in the context of mortgage-backed securities. Before I go on, I'll mention that a very standard reference on mortgage-backed securities is the textbook Bond Markets Analysis and Strategies by Frank Fabozzi, but I should advise you it is an extremely expensive book, and so I wouldn't recommend that any of you actually go out and purchase it. Still, if some of you have it, or if your local library or college library has it, you might want to take a look if you want to learn more about the mechanics of mortgages and how they work. So as I said, we're going to consider a standard level payment mortgage. We're going to assume, for example, that maybe there are 360 periods in the mortgage. So this is t equals 0, t equals 1, and so on, up until t equals 360. So this actually would correspond to a 30-year mortgage, because there are 12 months in a year, and so there would be 12 times 30 equals 360 periods in the mortgage. So we have an initial mortgage principal of M0. We're going to assume equal periodic payments of size $B are made in each period. So we're going to pay $B at the end of every period, and so on, until t equals 360, when the mortgage has finally been paid off. We'll assume that the coupon rate is C per period. So if you like, this is just the interest rate due each period on the mortgage, but we're going to use the term coupon rate for this. There are a total of n repayment periods. So in this example I've drawn up here, n is equal to 360. And then after the n payments, the mortgage principal and interest have all been paid. The mortgage is then said to be fully amortizing. This means that each payment, B, pays both interest and some of the principal. After all, if we make the same payment B in every period out until the end of the mortgage, then clearly each payment B is paying both some of the interest due on the outstanding principal, but it's also paying down some of the outstanding principal. So this is an important fact, and we're going to analyze this over the next couple of slides. We're going to use the following notation. We're going to let MK denote the mortgage principal remaining after the kth period. In that case, we can say that mk is equal to 1 plus c times mk minus 1 minus b. Now, where does this come from? Well, it comes from the following fact. The coupon rate is c per period. So if you look after period k minus 1, the outstanding principal is mk minus 1. Well, in the next period, the outstanding principal or loan will still be mk minus 1, but you will also owe an additional c times mk minus 1 of interest. So therefore, the outstanding principal will be 1 plus c times mk minus 1. But don't forget, you will also have paid $B at the end of that period. So therefore, the total outstanding principal after the kth period will be 1 plus c times mk minus 1 minus b. And that is true for k equals 0, 1, 2 up as far as n, the total number of repayment periods. But keep in mind, we said that the mortgage ends after n periods, when the entire mortgage has been paid off. So that implies that mn is equal to 0. And this is very important. So this last couple of lines here on the slide are very important. What can we say, or how can we use this expression here in 1? Well, what we can do is we can iterate it. For example, we know that m1 is therefore equal to 1 plus c times M0, the initial mortgage principal, minus B. We can now use this with k equal to 2. So M2 is equal to 1 plus C times M1, and M1 is 1 plus C times M0 minus B, and we have a minus B out here. So therefore this is equal to 1 plus C squared M0 minus the sum of 1 plus c times, well, let me put the minus here, and it's a b here, okay, to the power of j, with j equals 1, or j equals 0, up as far as 1. So now we could go on to m3 and repeat the same calculation to get m3 in terms of m0, b, and c, and so on. So that will leave us in general for k, we will get the following expression. We'll see that mk equals 1 plus c to the power of k times m0 minus b times the sum from p equals 0 to k minus 1 times 1 plus c to the power of p. We can simplify this. This is just a simple geometric summation here, and so we can just use our standard formula for the sum of a geometric series to get this expression down in 2. Now, we're not done yet. Remember that mn is equal to 0. After n repayment periods, the mortgage has been paid off. So if we take k equal to n, so take k equal to n in equation 2, and use the fact that mn equals 0, we will find that b is equal to the following expression down here. So this gives us b. And this is very interesting. Why? Well, it tells us that if we have a level payment mortgage, and we know the initial loan amount, or the initial principal M0, and we know n, the number of time periods, and we know the coupon rate, well, we can compute what the correct value of b is, so that b dollars paid in every period will pay off the mortgage after n periods. By the way, this is very related to the mathematics of annuities, which you saw back in the first week of this course. Anyway, moving on, we can substitute our expression for b back in up here, so we can put b in for this, and we can get this expression down here. And this is very nice because it tells us the value of the outstanding mortgage principal after k periods on the left hand side. That is equal to an expression on the right hand side which only depends on M0, the initial mortgage principal, the coupon rate C, the number of time periods in the entire mortgage N, and the current period K. Suppose now that we wish to compute the present value of the mortgage assuming a deterministic world. And by the way, what do I mean by deterministic world? Well, what I mean is that there's no uncertainty in the world. We're using a very stylized situation here. There's no randomness. There's no possibility of defaults or prepayments, though of course these are very important features in practice. Well, in that situation, we can actually compute the present value of a level payment mortgage. If we assume a risk-free interest rate of R per period, we obtain that the fair mortgage value is, and we're going to use F0 to denote the fair mortgage value. Then the fair mortgage value is equal to the sum of the b's divided by 1 plus r to the power of k from k equals 1 to the power of n. Now, just to keep in mind, R, you can think of R as being the borrowing rate for the banks that write the mortgages or that lend the money out to the homeowners. Presumably they can borrow at R, and for all intents and purposes here we can imagine R to be a risk-free interest rate. R in general will certainly not be equal to C. C is the coupon rate, or if you like the interest rate, that the homeowner must pay on their mortgage. R is the interest rate that the banks use to discount their payments. So in this case we're going to get F0 equals to the sum of the b's over 1 plus r to the power of k. Again, this is a geometric series. We can easily calculate this term, and then we can substitute in for b using our expression on the previous slide. If we do that, we'll get this expression here, expression number 5. Note that if r equals c, then actually F0 equals M0, because if R equals C, this term will cancel out with this term, and this term will cancel out with this term. And so, not surprisingly, we get F0 equals M0, and that's exactly as we would expect. In general, however, R is less than C, and that is because the banks who write the mortgages or lend the money out to the homeowners must charge a larger rate of interest, C, to account for the possibility of default, prepayment, servicing fees on the mortgages. They must make some profit. They must also account for payment uncertainty and so on. So in general, R will be less than C, and the difference here between R and C accounts for the difference between F0, the fair value of the mortgage from the bank's perspective, and M0, the amount of money that the homeowner is being lent in the first place. So in some sense you can think of F0 minus M0 as being the amount of money that the bank is earning from the mortgage, but that money must be used to handle these effects here, the possibility of default, prepayment, servicing fees, and so on, as I mentioned already. By the way, we're only working here with level payment mortgages, but you could do similar kinds of analysis with other types of mortgages, including adjustable rate mortgages or ARMs and so on. I also want to mention the fact that we can actually decompose the payment B that is paid in every period into an interest component and the principal component, and this is very easy to do. Since we know MK minus 1, we can compute the interest, let's call it IK, in every period. So IK is equal to C times MK minus 1. After all, MK minus 1 is the outstanding principal at the end of period K minus 1. So C times MK minus 1 is the interest that is due on that principal in time period K. So this is the interest that is paid in time period K. Therefore, that means we can interpret the kth payment, which is B, as paying PK equals B minus C MK minus 1 of the remaining principal. So IK is the interest that is paid at period K, and PK is the principal that is paid at period K. And of course note that IK plus PK is equal to B, which must be the case because we pay B dollars in every period. So that B dollars must be split up between principal and interest. And the way to split up is given to us up here and here for PK. So in any time period K, as I said, we can easily break down the payment B into scheduled principal payment and a scheduled interest payment IK. And we're actually going to use this observation later to create principal-only and interest-only mortgage-backed securities. These are an interesting class of mortgage-backed securities, and we will see that when we actually use a pool of mortgages to create these new securities, we're actually creating new securities that have very different risk profiles. But we will return to that in a later module. In the spreadsheet that goes with these modules in mortgage-backed securities, there are three worksheets. The first worksheet is called Single Mortgage Cash Flows, and it simply shows you how a single mortgage, a single level payment mortgage works. So that we can see everything here on the one sheet and the one screen, I've assumed that there's just 18 periods in the mortgage. In reality, there might be 240 or 360, and if I change it to 360, for example, we'll see that the actual spreadsheet adjusts appropriately. So we see that we get 360 months appearing. But just so that we can see everything in the same screenshot, I'm going to assume that there's just 18 periods. We start off with a mortgage loan of $20,000. The mortgage rate is 5%. Now this is an annual rate. This is not C. This is an annual rate, but we can easily convert it into a monthly rate, which is what we do here when we calculate the monthly payment. So this is B. This monthly payment in cell C3 is our B from the slides. So we see how to calculate B using C2, which is the monthly rate, as well of course C1, which is M0, the initial mortgage loan. So what we have here is we have the 18 months. We see the beginning monthly balance. This is the outstanding principal on the mortgage at the beginning of each month. We see the monthly payment is $1,155.61. It's the same monthly payment in every period. And as we saw on the final slide, we can break this payment down into a monthly interest payment and a scheduled principal payment. So that's what these quantities are here. Note that the monthly interest and the scheduled principal always sum up to the monthly payment. So in any cell here, you'll see that these numbers always sum up to the corresponding cell in column E. So monthly interest plus scheduled principal repayment is equal to the total monthly payment. And then of course, in order to get the ending mortgage balance, we simply subtract the scheduled principal repayment from the monthly payment. And of course, after 18 periods, the outstanding mortgage balance is 0 at the end. So you can play with this spreadsheet if you like. As I said, in practice, you typically have a much longer term of the loan. Instead of 18 periods, you might have 240 for a 20-year mortgage, or 180 for a 15-year mortgage, or 360 for a 30-year mortgage. Another interesting observation to make is that in the earlier part of the mortgage, the monthly interest payments are larger than they are in the latter part of the mortgage. So up here you see in the earlier months of the mortgage, the interest payments are around $80, $75 and so on, but they're much smaller later in the mortgage. On the other hand, the principal repayments in the earlier part of the mortgage are smaller, in this case around $1,075, $1,080, versus later in the mortgage when they're $1,141, $1,146, $1,150. The impact isn't so obvious here, but if I switch to say a 360 period mortgage, you'll see that this effect is much greater. So here, and let's make it say a $200,000 mortgage. So here what you'll notice is the monthly payment is $1,073, but most of that payment is going to pay interest. Look at that. Of that $1,073 in the earlier part of the mortgage life, most of that is going to pay interest, and only a smaller fraction of it, maybe on the order of 25%, is going to pay principal. However, if I scroll down towards the end of the mortgage, which is a long way down because it's 360 months, then you will see that now only a small part of the monthly payment is going to pay monthly interest, and that's because the outstanding principal is much smaller in these time periods, so a much smaller interest amount is due, and a much larger fraction of the monthly payment is going to pay the principal. And this observation is important. It's worthwhile knowing for anybody who's thinking about taking out a level payment mortgage, that in the earlier part of the mortgage life, most of their monthly payments will actually be going towards paying interest, and only a small fraction will be going towards paying principal. That will be reversed towards the end of the life of the mortgage. This, as I mentioned earlier, will also have a significant impact when we create principal-only and interest-only mortgage-backed securities and see how they are constructed.